Okay, so this is the video for day 2 of related rates notes. And before we start working examples, I just kind of want to recap the process that we followed through yesterday when we were solving some of our related rates problems. So I'm just going to kind of write out those steps, and then we can come back and we can use those steps to work some more examples. So the first thing that we want to do in any of these problems, obviously, is we need to read the problem so we know what's happening. So read the problem. Sounds like kind of an obvious step, but sometimes we kind of skim over that and we miss some of the important elements of the problem that we need. So make sure you read the problem carefully so that you can correctly identify what it is that you're going to be solving for. Then after I've read the problem, I like to kind of take the problem and, if I need to, translate it into a picture. So step 2 is to draw a picture. Sometimes once we draw the picture, we get a better idea of what it is exactly that's happening in that problem. Then we also need to identify what rate of change we're given and what rate of change it is that we're looking for, because how we set up our equation that relates those two things is going to depend on what we know and what it is that we want to know. So step 3 is to list the rate that you're given. So what rate of change do they give us in the problem? And the rate you want to find. So what rate of change is it that I'm going to be solving for? Then once I know those two pieces of information, I'm going to start to look for some kind of equation that I can use that relates those two things. So what do I know about what's changing? What do I know about the other thing that I'm looking for, how it's changing, and how do those things relate to one another? So step 4 is to write an equation relating those two. Step 3. Now, hopefully when we get to this step, our equation just has the variable whose rate we know something about and the variable whose rate we don't know something about. But as we saw in that last example yesterday, that's not always going to be the case. So if we have extra information, some rate or some variable that we don't know about, then we need to eliminate that variable somehow. So in that case, we need to use some other equation to try to get down to one independent variable. So I'm going to use another equation to get to one independent variable, if we're not already there. Once we've gotten down to the variable we know about and the variable whose rate we want to know about, then at that point we're ready to actually relate those two rates to each other by taking the derivative. Once we've taken the derivative, then we can take the information that we're given and substitute to solve. And then, of course, once we have that information, once we have solved, we can take our solution and we can just kind of clarify what it means in context to the problem by writing a sentence that has our answer with correct units. And remember that sentence, we need to say what it is that's changing. How is it changing? Is it increasing? Is it decreasing? By how much? And with correct units. So that's just kind of a quick recap of the steps that we used yesterday to solve. We're going to be using these same steps for all of our related rates problems. Some steps we might be able to skip just depending on the problem and whether or not, for example, we have just two variables that we're relating or more than two variables. I do want to point out another big thing here. Notice that in this list of steps that we are following, we're not actually substituting information until the very last step. That's a really important thing. If you substitute information too soon before you've taken that derivative, you're going to be getting the wrong answer if it's something that could change. So for example, if something is changing in the problem and you substitute in a numeric value for that thing that's changing before you've taken the derivative to account for that change, you've taken a variable that's changing and you've substituted in a constant, which means that you're either going to end up with a derivative that's a constant multiple or possibly a constant itself, in which case the rate of change would be 0. So if something is changing in this problem, you cannot substitute a value in for it until you've taken the derivative and you've accounted for the fact that that thing is changing. Otherwise, you're not going to end up with the right results that you need. So we're going to take these steps and we are going to apply them to some more problems. So let's look at this first problem. It says that a fish is reeled in at a rate of 2 feet per second from a bridge that is 16 feet above the water. At what rate is the angle between the line and the water changing when there's 20 feet of line out? Okay, so I read the problem. Then I'm going to draw a picture. So I have somebody fishing from a bridge. So here's my bridge. They tell me that the bridge is 16 feet above the water. And the person at the top of the bridge is reeling in a fish. Well, there's my fish. We want to know what is the rate of change between the angle between the line, so between the line and the water. So if this is my water level, we're looking at the rate at which the angle between the line and the water is changing. So I need to give that angle some name. I don't have a numeric value because that angle is going to change as I'm reeling in the fish. So I'm going to go with theta, because theta is usually what we use to describe an angle. So I have this triangle. In fact, I have a right triangle here. And I'm reeling this fish in. And as I'm reeling the fish in, my line length here is changing. In fact, they tell me that is being reeled in at a rate of 2 feet per second. That's the rate of change that they've given us. That feet per second is the rate of change that they've given us. And they're telling us how quickly the length of our hypotenuse, in this case, on our right triangle is changing. Because as we're reeling in this line here, this distance between the bridge and the fish is going to be decreasing. So we need some kind of variable for that. I'm going to call the length of the line x. Again, we can call it whatever we want, but x seems to work nicely. So if we are reeling in the line, then we are given the rate of change of the length of that line, x, with respect to t. And they tell us that that line is being reeled in at a rate of 2 feet per second. Because the line is being reeled in, the length of the line is decreasing. So that means that the rate of change of the length of the line, x, should be negative because the length of the line is decreasing. We want to find the rate at which the angle between the line and the water is changing. And we're calling the angle between the line and the water theta. So we want to find the rate of change of the angle between the water and the line, theta is what we called it, with respect to t, when there's 20 feet of line out. So when the length of this line, x, is 20 feet. So we read our problem, we drew our picture, we listed the rate that we were given and the rate that we want to find. And now we want to find an equation that's going to relate those things to each other. So I have a right triangle. I have an angle in that right triangle that's not the right angle. I'm looking at the hypotenuse, x, changing. And I know the length of the side. Now, as I said before, if there's something in the problem that's changing, some kind of value that changes in the problem, we don't want to substitute in until we've taken the derivative. So this 20 feet of line, I can't put in for x because x is a value that's changing. However, the bridge is 16 feet tall, and it doesn't matter what our angle is, and it doesn't matter how much line we have out. The height of the bridge will be constant. It's always going to be 16 feet. That means that I can use this 16 feet from the very beginning. I can use it before I've taken the derivative because it's not going to change. Its rate of change is going to be 0. So I can use 16 right up front. I just can't use the 20 feet until after I've taken the derivative because that 20 feet is going to be something that's changing during the problem. So the relationship that I'm going to use here for this angle and this length of my right triangle and the hypotenuse, I have the opposite side of the right triangle and the hypotenuse. And I know that the sine of this angle is going to be equal to opposite over hypotenuse. So I have that the sine of theta will be equal to the opposite side, which will always be 16, over the hypotenuse, which I called x because it's changing. So I've come up with an equation that relates the two things. I know about the rate of change of x, it's in there. I want to know about the rate of change of theta, it's in there. And the good news on this one is I get to skip the next step because I don't have to worry about eliminating any extra variables. I want to know about d theta dt, I know about dx dt, and I don't have any other information in there. So at this point, I can go ahead and I can take the derivative. Now I'm going to go ahead and write this as 16x to the negative 1, just to make it a little bit easier in that next step when I actually differentiate. Now I'm going to take the derivative of sine of theta with respect to t, and 16x to the negative 1 with respect to t. The derivative of sine of stuff is cosine of the stuff times the derivative of the stuff with respect to t. The derivative of 16 times stuff to the negative 1 will be negative 16 times the stuff to the negative 2 times the derivative of the stuff with respect to t. So we have that cosine of theta times the derivative of theta with respect to t is equal to negative 16 divided by x squared times the derivative of x with respect to t. So now that I've taken the derivative, now I can start to substitute in the things that are changing. In this problem, I'm wanting to know what is d theta dt when x equals 20 feet. So then I can start substituting in. I don't know what d theta dt is. That's what I'm looking for. But I do know that I'm looking for that when x is 20, so we'd have 20 squared. And I do know that the rate of change of x with respect to t, we said was negative 2 feet per second. over here, this d theta dt is what I'm looking for. But then I run into a little bit of a problem here with this cosine of theta. I don't know what theta is. And I might be able to work backwards and figure it out, but I really don't need to know what theta is at this instant. I just need to know what cosine of theta is at this instant. So I'm just going to kind of come over here and redraw what I have happening. This is my right triangle. Again, we know that the bridge is a constant 16 feet tall. We know that this angle is the angle that we're looking at, theta. And we want to know what is cosine of theta when x is 20 feet. Well, if the hypotenuse is 20 feet and this leg of my right triangle is 16 feet, then really I have a 3, 4, 5 triangle, right? Because this will be 4 times 4, this will be 4 times 5. So this side should be 4 times 3, which will be 12 feet. If you don't immediately see that you have a 3, 4, 5 triangle, you could also get the same number just by using Pythagorean theorem. So again, I don't know what theta is, but I can find cosine of theta, because cosine of theta is going to be equal to the adjacent leg, 12, over the hypotenuse, 20. Or, if we reduce that, 3 over 5. So even though I don't know what theta is, I know that at the instant when x is 20 feet, cosine of theta will be 3 over 5. And that is everything that I need to start solving for theta. So now, let's see, we'll go I know that d theta dt is equal to negative 16 over 400 times negative 2 over 1 times 5 over 3. And I'm going to go ahead and reduce this as much as I can before I multiply. So here I would have 2 times 5 is 10. And so I could reduce the 2 and the 5, that 10, with the 400 to get 40. I could also go ahead and reduce the 16 and the 40 by a power of 4. So that would be 4 and that would be 10. And I'm not sure what else I could reduce here. Oh, no, I could reduce those even further because 2 goes into 4 2 times, 2 goes into 10 5 times. So on top I've got a negative 2 times a negative 1 would give me a positive 2. And on bottom I've got 5 times 1 times 3. 5 times 3 is going to give me 15. So I have that d theta dt is 2 over 15. When you're dealing with angles in related rates problems, we are always going to be coming up with units where the angle is going to be measured in radians. There is a really good reason as to why that is, but it's a little bit beyond the scope of this class and it's kind of difficult to follow. So I'm just going to tell you that if you want to look into it a little bit more, you can. In fact, I think our textbook even discusses a little bit why it would be in radians, or you could just take my word for it that the angle will be in radians. And our time measurement originally was in seconds, so that part didn't change. We're talking about radians per second. So if I wrote this out as a complete sentence, I would say that the angle is increasing because its rate of change is positive at a rate of 2/15 radians per